Hi there, welcome to Uncle B Studio, where you learn how to act like a grandpa but code like a pro. Last video, we fine-tuned the GPT-3 model with customized data, but results wasn't ideal. So today we're going to try to improve our previous Warren Buffett model using embeddings. We're going to go over the basic of OpenAI embedding, what they are, how they work, and we'll show you how to use them to improve our Warren Buffett models. Let's get to it. First, let's start with the basics. What are embeddings? Well, embeddings are a set of language models that are capable of representing words and phrases as numerical vectors. These vectors can then be used to calculate the similarities between other words and phrases, making it possible to perform more advanced natural language processing tasks like sentiment analysis or language translations. Here is an example. Say if you're building a menu recommendation system using neural networks. Embedding can then be used to group all the similar menu items together in a vector space. For example, shrimp fried rice and chicken fried rice are grouped together. Fried chicken, chicken waffle, and burgers, they're grouped together. And say if user wants a dish similar to fried chicken, the model can return either chicken and waffle or burgers to the users. Note that embedding can be customized specific to a model. For example, fried chicken and chicken fried rice, they might be very similar in terms of the text, but based on our training data, say purchase history, they're not considered as similar at all. And the common embedding model include principal component analysis, Word2Vec, the classic, BERT, B-E-R-T, universal sentence encoders, and new ones like Google T5. OpenAI provides embedding features based on their own models. Usually cheaper the models, there's less dimensions, although higher dimension doesn't necessarily mean it's better. Now we have a basic understanding of embedding. Let's start on the model. As for any type of machine learning problem, we need to acquire our dataset. We looked at historical Warren Buffett codes previously, but the data is not up to date. So today we want to explore a richer dataset. Luckily, CNBC has compiled a Warren Buffett archive, which you can find here. Each year, the annual meeting is broken down into mornings and afternoon sessions. And you can find all the transcripts and videos on the webpage. We first need to obtain the list of URL for each meeting page. Then we can write a simple Python script to parse each chapters and speakers to store the results, which is very similar to what we did in part 1. So based on the card, we can see each of these meeting cards, it will contain a URL for a specific meeting. For example, this one here. Looking at the code, we use Beautiful Soup again. We'll go through all the meeting cards and get a list of URLs for both the morning and the afternoon sessions. And then we'll parse each of the page using our function called parse CNBC official transcript. Now, I'm going to skip the implementation details, but we will definitely publish the code in a GitHub repo for everyone after the series is completed. For now, this is how it will look like if you run each of the functions. We can then dump the data in an Excel just to get a sense of how the format will look like. An example will be the clipboard, bring up your Excels. And you can see we're parsing all the contents of each of the sections and also including the category as well. And the content should match the web page exactly. For example, this is the transcript for the 2020 annual meetings. If you look at the web page, the content should be exactly the same. Now we have our data ready, let's think about how we can build an improved version of the model. First and foremost, let's design how we're structuring the project. We first calculate the embedding for all of the transcript we've downloaded, And when a user asks us questions, we'll find the embedding for the questions as well. And then we'll do a search in our transcript to find one or more most relevant topics. We'll use these topics as context text, do some prompt engineering to limit the hallucinations, then pass to the completion model we're using in part 1. Now we have a plan. First step is to calculate the embedding for a block of large text. Let's first create a Python function, call the OpenAI embedding APIs, and pass in the text. I'm going to call this function getEmbedding in my code, and I'm going to call it the API and return the results. Now, once you pass in a text, the results should be lists of numerical values, and these representing the embeddings and vectors. You can actually find the list of the models in here. Then we will append embedding to each section of Warren Buffett's transcript. So I have a function called @embedding to WB transcript, and it basically takes in our data, calculate the embeddings, and append it to our data frames. Now, we might run into an issue if the text is large, and then the error might say this model's maximum contact length is 8,191 tokens. However, you're requesting 8,460 tokens. This really is a OpenAI model limitations. Therefore, before we calculate the embedding, we should also count the number of tokens for our text. We can either skip it or break it down to smaller chunks, if the text is too large. And speaking of tokens, it basically breaks down a large text block into smaller segments and identify type of each segment so it's easier for code to digest. You can find an example here. For example, if you enter Cocaine Bear is a great movie, I watched it yesterday, you can see the resulting tokens from the sentence that I just put in. The rule of thumb here is that the number of tokens is roughly 4 characters of text and 3/4 of a word. So if your text have a length of 400, you just divide by 4 and you get roughly about 100 tokens. And if you have 100 words, then you have about 133 tokens. And now we can calculate the number of tokens. If it's too long, then we can actually skip it. And this is why in the code, we're skipping some of the large text in the transcript. This whole process does cost a little bit of money. It's about $1 or $2, but hopefully it will be covered by your free credit from OpenAI. And if you run the functions, this will add an OpenAI embedding columns to each of the topics that we have. So for example, if we look at the results of the data frame, there should be a column now called OpenAI embeddings. The next step, if you look at our architecture diagram, we need to do a text search, or in this case, a vector search. The idea is that giving a question, let's see if we can find the relevant topics based on the embedding. The question really boils down to, how do I find similarity between two vectors? There's usually 3 approaches: 1, Euclidean distance; 2, cosine; 3, dot products. We're not going to go through details on how it works for each one of them, but usually we would like to use cosine similarities because our question might be short and the relevant topic discussion may be very long, right? This is because dot product similarities cares both the angles and magnitude in the vector space, where cosine similarity only cares about the angles. However, because the output for OpenAI embeddings are normalized to a unit vectors, i.e. the length of 1, the cosine similarities and dot product similarity is the same. Therefore, we can use dot products because it's much easier to compute. In terms of code, this is pretty straightforward. We use the dot function from NumPy and passing in 2 lists of numeric values. And then we can use this function to rank based on our transcript. So we'll look through our transcript, giving a question, find the topics that are most relevant. So for example, if we're asking, what do you think about technology company? Is it investable? And find the top 2 most relevant results, and this is the result we get. As you can see, the results are decent. All the highestly ranked conversations seem to be surrounding software and tech stocks. And if you have a large data set, looping through it to find a similar text might not be the best idea because it's going to take a while. So at that point, you might want to use a vector database or search engines like Pinecone, Waviate, Milvus. If you guys want to know more, I'll post the links in the description below. Now we want to get back to our completion model and add the most similar text as context to our model to see if our model will actually talk more like Warren. But in order to do this, we need to do a little bit of prompt engineering. If you go back to our architecture diagram, this is the prompt engineering section in the workflow. We would like to structure the prompt as follows. Answer the question as truthfully as possible using provided text as a guidance. Provide a longer explanation if possible. And if the answer is not contained in the text below, say, I don't know. Now we have this function that does a little bit of prompt engineering and also send the context and the question to the completion API and they get the results back. We're ready to tie everything together. And start from a question, find context based on a vector search, and then pass the context to completion model to get the results. So we will get our data, we'll find the most relevant topics, then we'll call the combine embedding completion function, which is the function we just saw, and then we'll return the results. There are several limitations on this. So for example, if the context text block is too large, then you will have a token limitation errors. The error will say this model's maximum context length is 4,097 tokens. However, your requested token is bigger than that. This is because both the prompt and the context for completion are both counted toward your token limits. Now we have our model, we can start playing around with it. For example, if you want to know what Warren Buffett think about Silicon Valley bank failures and other bank failures, you can ask him that question. The question text will be, what do you think about the bank failure? And then you can ask them the questions. And here is what the model output look like. I think the government should not allow banks to collapse immediately and should have system in place that makes it very painful for the people involved if a bank failure does occur. I also think that reducing leverage in the system is important and that the board of directors of banks should suffer penalties for any failure. However, I think it is likely that there will still be too big to fail institutions in the future. That sounds very much like something Warren Buffett would say in his annual meeting. And that's it. Today, we've improved our Warren Buffett model using OpenAI embeddings. And in the coming episodes, there's several other topics that we want to talk about. One is completion model from Google Bar, Corapo, Anthropic Cloud, etc. And also, we want to talk about the recent release of GPT-4. And finally, we want to see how we can deploy our Warren Buffett model as a web application so anyone can ask the questions. So stay tuned, like and subscribe, and I'll see you next time.